All right, chapter 6 today. It's actually haven't changed. Monday, 04. All right. What does this remind you of? Seriously, did I hear washing machine? You're college students. I know you're all busy, but come on. Should be having the time of your life while you're studying. Engineers are known to work hard, study hard, and party hard. That represents a speaker. It's a speaker box. It's a three-way speaker box. Okay. What is this called? Kind of mid-range. What is this called? Not a sub, but just a woofer. How about this? Tweeter, unlike the Twitter, this is for mid-range. Subwoofer is a separate, well, it's a separate box for technical reasons. It's basically produces the loud thumping noises that you would hear in music, or if you're watching an action movie, the explosion sounds, the very deep bass sounds. Anyway, the point to this is the speaker box, if you look behind, has only two connectors. So if you look behind the box, there would be two connectors, one for positive, one for negative. It has polarity, but the polarity does not actually matter unless like the system is grounded and there's a, there's like external noise signals that need to be shielded from the actual circuitry. So the point I'm trying to make here is we have three drivers. These are known as drivers. So there's three drivers, 1, 2, and 3. And you have one connection going into the speaker box, right? And each one of these drivers actually has two terminals. If you open up the back of any speaker, which is not that difficult to do, you have two screws somewhere around here. You open it up and you'll see two wires going in. These two wires go in, and there'll be a, depending on the, well, make and model of the speaker box and how expensive it is, it will go into a circuit. That circuit will have some capacitors, some resistors, and some big inductors. Again, depending on how much money, it costs. So that circuit could be very, very small, or it could be very big, depending on the quality of the components, depending on the design. But what that circuit does is it splits that incoming signal into three different zones, into three different parts. And what it is actually doing is it is filtering out unwanted signals and separating into three different components for those three speaker drivers. So it goes into this circuit, and the output is 1:3. One of the outputs goes to a tweeter, the other one goes to the mid-range for vocals, the other one goes to the woofer. The woofer reproduces low frequency signals, the loud thumping noises that you hear, the deep bass signals. The mid-range, of course, is for vocals, and the tweeter is for high frequency signals. Okay, high frequency signals require a lower, smaller physical size of a tweeter. So this circuit is known as a crossover network. It's a crossover network. Okay. In electrical engineering, it is simply an electrical filter. filter. It is a circuit that is made up of inductors and capacitors and resistors. It's a RLC circuit. And it uses the frequency dependence of a capacitor and inductor. So we saw in chapter 5 that the impedance or the reactance of an inductor and a capacitor varies with frequency. For an inductor, it is directly proportional to the frequency, and for a capacitor, it is inversely proportional. So when you have a circuit like this, what it does is, depending on the incoming frequencies, it can filter out, it can block out certain signals and allow certain other signals to pass through. This circuit, by the way, an electric filter, is the foundation of everything that we use in the world today. Well, foundation as in it's a critical key component without which nothing would actually work. Okay. There are frequency signals all around us, whether they are wired or wireless. We have frequency signals all around us. If you put our hands up in the air right now, maybe actually even without putting your hands up in the air, our body is a receptor for all these signals. There's television, radio, satellite, mobile. These are all just the common wireless signals that are all around us right now. So if you have a phone, whether it's a smartphone or a regular phone, it's communicating wirelessly with a cell phone tower outside. But there are three major companies that have three different signals coming in the air, right? You have Verizon, T-Mobile, and AT&T. So if you have a Verizon phone, how do you make sure that it only works in the Verizon network? It doesn't work on anything else, right? The phone is receiving signals right now from Verizon, AT&T, and T-Mobile. So what they do is they broadcast at a certain frequency. You've heard that the phone is locked, right? The phone is locked to a network. The first things they do is make sure they broadcast at a different frequency so there's no overlap between different wireless carriers, right? And that's basically the broadcast signals that you see here. This is known as a frequency spectrum. So each company buys this spectrum from the government. And every country, it works exactly the same way. The government controls the airwaves. So the government of each country sells a frequency spectrum to a company. They have an auction for this. Companies bid on this and they buy this wireless spectrum for a certain period of time. And they are the only ones who are permitted to use that frequency spectrum. So they broadcast on that frequency spectrum. And then the companies, what they do is they install a filter at the front end of any wireless device, which will only allow DR signal to go into the device. Everything else is filtered out and blocked. So Verizon will block out all signals except for their own. And so only their signal is allowed or permitted to go inside their phone. AM and FM radio. AM stands for amplitude modulation. FM stands for frequency modulation. Again, technical term for, you don't need to worry about that. But have you ever heard of 101.7 FM or 680 AM? That is the broadcasting frequency of that particular radio station. AM broadcasts in a kilohertz range, 1000 hertz, right? So 680 AM stands for 680,000 hertz. It is broadcasting a frequency signal, or it is broadcasting that voice signal modulated on top of a frequency signal that is spinning 680 times in 1 second, which, by the way, is not that large a frequency considering everything else that we use. 101.7 FM is basically a frequency signal that is being broadcast at 101 megahertz, 10⁶. So you have our common broadcasting signals right here. AM is the kilohertz range, FM is in the megahertz range. There's television signals that are broadcast over the air, which is known as OTA, over the air signals, right? You can hook up a rabbit ear antenna and just capture television signals coming over the airwaves. That's free TV. The 4 major broadcasting television stations, Fox, ABC, NBC, and CBS. They're all broadcast over the air. So each one of those is broadcasting at a certain frequency. And when you set your television to a certain channel, what you're doing is you are blocking out all other signals except for that particular television station. And it's not magic. What allows this to happen is basically a filter at the front end. Okay, an electronic filter at the front end blocks out all unwanted signals. And that's what we're going to study in this chapter. Okay, one important point I'm going to make. We will have one final quiz next week based on chapter 6, which is what we're studying right now. I will not assess chapter 6 on the final exam. Okay, so there are 3 homework assignments associated with chapter 6. Is it 3 or 2? 3. So you get done with those homework assignments, you do the quiz next week, and that's it. I will not assess it separately because that is enough assessment. Okay, so no chapter 6 on the final, and I will change the final exam sheet to reflect that. Okay, so as I was saying, the filters, electronic filters, use the property of inductors and capacitors of the property of their impedance varying according to the frequency, right? So the title of the chapter is frequency response. We are studying the frequency response of electronic circuits. Let's see. So far you have studied circuit analysis where you're used to a power source connected to certain components, could be connected in any manner, whether it's series or parallel, right? And you would be measuring the voltage or the current through these components. You don't have to draw this out. This is just for explanation purposes. Okay. But now for this chapter, you're going to have to think in terms of a port. Okay, a port. A port is nothing but two or more sets of wires or terminals connected together. Okay. So this power supply had 2 terminals, right? Positive and negative. Positive and negative. If you take those terminals and pair them together, we call it a port. Okay. And because the power supply is supplying energy to the rest of the circuit, meaning it's going into the circuit, we label this as the input port. So these 2 terminals together comprise an input port. And then any point in the circuit where you obtain an output would be an output port. In this case, we are treating the right side of the circuit as the output port. But again, those 2 terminals put together comprise the output port. And hence, it is known as a 2-port network or a 2-port circuit. There's an input port and an output port. So again, in circuit analysis so far, we have learned we are dealing with currents and voltages for individual components. Now we have to think of a pair of terminals connected together. Nothing is changing as far as analysis goes. Okay, it's just a different approach to dealing with a circuit that has multiple components, and you want to deal only with input and output. And you can think of this as a sealed box, and we have no idea what's inside the box. We only know what the box does. Okay, we only know what the box does, but we have no idea what is actually inside the box. And so if you're analyzing a circuit, you would know what it does, but you don't really care about how it's doing it or why it's doing it. So for instance, an amplifier can be considered as a network. We don't need to know the internal circuitry. We only need to know what the gain of that amplifier is. If you know the gain of an amplifier is set to like 10, then no matter what the input is, you can predict or calculate the output, right? If for instance, an amplifier has a gain of 10, if I tell you the input is 1, what is the output? 10, right? It amplifies the incoming signal 10 times. So if I tell you the input is like 2, you know it's 20. If it's 0.5, then it's 5. So again, it's a sealed box, and we don't know what's inside the box. We only care about what it's doing to the incoming signal. With regards to electronic filters, what they are doing is you have multiple signals coming in, right? Those signals do not have any concrete shapes, again, because they're all mixed together. As I said, there are wireless signals in the air all around us, whether it's wireless or whether it's wired, as in a speaker box. All of these all of these signals have different frequencies, so they're all coming in at the same time. So there is no specific shape. It's just a mixture of all these signals coming together. What a filter does is it separates out these signals into different components. In this example or illustration, we are just showing two parts. We're just showing that the signal is being separated into two parts. And each part or each component is affected differently depending on the function of that sealed box. Okay, depending on the function of the sealed box. So for input component 1, V in 1, we have a different output. For the second component, V in 2, we have a different output. Component 1 or V in 1 is being enhanced, is being amplified. Amplified or enhanced. This one is being attenuated or blocked. Now, when I use the term block, no real life filter can block something 100%. There's always some minimum component that could slip through, right? Depending on the design, depending on the components, nothing can ever be 100%, but we can try to get as close as possible to 100%. Okay. So you can see V in 1 is being amplified and V in 2 reduced. And then finally, you sum it up again at the output, and what you obtain is basically V in 1. Okay. V in 2 is on a much reduced scale. So the input signal is being transferred to the output by that circuit or by that network while performing some function on it. Okay, while performing some function on it. So we introduce a term known as transfer function. Okay, transfer function. Again, this is a sealed box. We don't know how it works, but we do know what it actually does. And that is from the term h of f, the transfer function. It simply describes the ratio of the output voltage to the input voltage. It's the ratio of the output to the input, V out or V in. And if you notice, these are phasors. So they are complex quantities. So h of f, the transfer function, is a complex quantity that has magnitude and phase. It is a ratio of the phasor voltages input to the output. Okay. I discovered it and named it after me, but that's not really true. H of f, actually, there's no consensus of why it's used h of f. There are some theories that it's just random, picked at random, because we were already using E, F, G, and the next letter was H. But, I've asked around, I've read about it. But there was one opinion online which said it was named after a German physicist whose name started with an H. So I don't know. Anyway, it's a complex quantity. It simply describes how the input is being transferred to the output, hence the term transfer function. Okay, the sealed box is performing some function, and that function is described by h of f, the transfer function. So again, as in the example of an amplifier, h of f would simply be 2 or 5 or 6. Doesn't really matter what the value is, as long as we know that it's amplifying, right? And because it is a ratio of voltages, it is unitless. Okay, it is unitless. All right, let's take a 10-second pause. Let me know if you have any questions. Everyone good so far? Okay. So let's look at an example. Here's a graphical illustration of what a network is doing. It is describing the magnitude in the diagram on the left, or the chart on the left, and the phase, the chart on the right. The question is, what is V out of T? Now you have to pay attention to what the question is asking you. It is not asking you for the phasor V out, it's asking you for V out as a function of time. Okay, so your final answer has to be as a function of time. And V in of T, V in of T is given as, actually, let's see, 3 volts. Oops, I forgot 3 plus, there we go. 3 plus 2 cos of 2000 pi t plus cos of 4000 pi t. Minus 70 degrees volts. All right, and we are asked to find V out of T. So how many components does this input signal have? 3 different components. It has 3 separate components. And we'll use this example to see how it filters out each one of these components, depending on this transfer function, right? So the transfer function, again, is describing the performance of a network. We don't know what the network is. We don't really care. We just know what it is doing based on the information given to us in these graphs or in this chart. At every frequency, the response is different, right? The response is different. So we need to find out the frequency of each component and then look at the transfer function and determine what it is doing for each component. So V in 1 of T, V in 1 is simply 3 volts. So what is the frequency? What is the frequency F or F1? It's a number, it's a constant number. What is the frequency? It's 0. It's not varying at all. It's a constant. So it's a DC value. So F is equal to 0 hertz. So I'm talking about this component right here. There are 3 different components. There's 1, there's 2, and there's 3. Components 2 and 3 are a function of time. The first one isn't. It simply has a value of 3. That's it. So if it's just a number, it is not a function of time. Frequency F is equal to 0. It is simply a DC component along with the AC signal or the time varying signal. V in 2 is 2 cos 2000 pi t. So F is equal to, what is F2? F2 would be omega 2 divided by 2 pi, 1000 hertz. Omega is 2 pi F. So you take the standard expression and you equate it to Vp cos of omega t plus or minus theta. So 2 cos 2000 pi t, you equate 2000 pi equals 2 pi f, and you get f has a value of 1000 hertz. The reason we are changing it into hertz is because the information presented to us in the chart is frequency f in hertz. And similarly, we would do the same for the third component, and we'd obtain cos of 4000 pi t minus 70 degrees. F3 would be omega 3 by 2 pi. It would be 2000 hertz. Okay, we are extracting information from the problem statement, and we have F1 is 0 hertz, F2 is 1000, F3 is 2000. So then we come here, and this is of course 0, this is 0. You're going to write the transfer function, the value of this transfer function at each one of those frequencies. So H at 0 or H of 0 is 4 to the angle of 0. And so it's simply 4. H of 1000 and H of 2000. At 1000, it has a value of 3 and 30. And so 3 with an angle of 30 degrees. And then at 2000, it has a value of 2 with a phase angle of 60 degrees. Does that make sense? We need to know what that circuit or what that network is doing at each particular frequency, right? We could have like 10 different components in the incoming input signal. The first thing we'd have to do is equate it with the standard expression, Vp cos omega t plus or minus theta, figure out what the frequency f, right? Figure out the frequency, what the value for f is, go back to our chart, extract the information about the magnitude and the phase for h of f at each particular frequency. So incoming input signal has three components: 0 hertz, 1000 hertz, and 2000 hertz. We go to the chart and we obtain h of f as h of 0, h of 1000, h of 2000 with the values 4, 3, and 2. Now all that's remaining is to apply the equation V out, phasor for V out would simply be given by h of f times the phasor for V in. So V out 1 would simply be h of 0 times V in 1, or phasor for 1. Actually, we never wrote out the phasors here, so let's go ahead and do that also. Phasor for V in 1 is nothing but 3 volts. 2 would be 2 angle 0. And for 3, it would be 1 with an angle of minus 70 degrees volts. Okay. So this would simply be 3 times 4, 12 volts. V out 2, similarly, is the product of h of 1000 times V in 2. That gives me 6 with an angle of 30. And V out 3 is 1 with minus 70. Oh. 2 angle 60 times 1 angle minus 70 gives me a magnitude of 2 with a phase angle of minus 10. Okay. Look at the input and the output. Input component 3 at 0 hertz is amplifying the signal by a factor of 4. And so the 3 volts turn into 12 at the output. We have 3 volts here. And at the output, it turns into 12. Okay. So lower component has been amplified. If you look at 1000 hertz, 1000 hertz had an amplitude of 3, and now it's 6. So it's amplified a little bit, but not as much as 0 hertz. And then 2 remains the same. It's not being filtered out at 2000. So only the phase is being altered, but the amplitude is not. If you look at the chart right here, beyond 2500, hertz, the amplitude or the magnitude of the function goes to 0. Meaning if there was an incoming input component that had a frequency value of 2500 or higher, the output for that would simply be equal to 0. So it's blocking all frequency signals or all frequency components 2500 hertz or higher value. Does that make sense? And so it's working as a low pass filter. It's allowing the low frequency signals to pass through, and it's blocking all the higher frequency signals. Okay. All right, questions? Any questions at all? There's one final step remaining, which is to write the time domain expression. And so V out of t would be equal to 12 plus 6 cos of, you have to go back to the original frequency. So 2000 pi t plus 30 degrees plus 2 cos of 4000 pi t minus 10 degrees and volts. Yeah, that's not going to work. I'll leave it there. Okay, if there are no more questions, we'll end class here today. There's a homework associated with this, with the material that we just covered here. I think there's just two problems online. One is a short concept, and the other one is a problem that's exactly similar to this one. So it shouldn't take you longer than 10 minutes to get it done. If you have time now, like if you have half an hour or an hour before class starts, I would suggest go ahead and just review this material right now and get done with that homework. All right, I'll see you all on Wednesday.
The way the signals are like, it breaks it up into like different sine waves, right?
It doesn't break it up. That was just kind of like an analogy to show how it's handling different components. So it doesn't actually break it up.
Professor?
Uh-huh. Is that something that's gonna be coming next?
Cover, so break up the incoming signal in filters.
Yeah, because that's like kind of what was kind of showed like we did that.
Oh, okay, I see. Like low pass filters, and yeah, we're going to cover that in this chapter itself. Yeah.
Professor?
Yes.
So I turned in my quiz, right? I realized like I was about to turn it in a second time because I saw some mistake.
You send me an email about this. You're on speaker right now, so I cannot ensure your privacy. So
Okay.
send me an email about this, please.
Okay, cool.
Yes.
So for finding VR,
Uh-huh.
you wrote these out, but then you had to skip it because you're short on time. But when I calculated it, I did not get these same values. So I was wondering, like, so VR equals VS times R over ZEQ. So do you just do 100, like the resistance
Yep.
is 100 ohms
Yep.
over ZEQ?
Yes.
Because I was getting,
You should get the same answer that we obtained here. What is the EQ? Let's see.
ZEQ is 141.
Or 5. And what value does VS?
So this would be
VS
100
times. So what is the phase angle for VS?
VS.
30. 30 minus 45 gives you minus 15. So that's minus 15 right there. And then R is 100, right? 100 divided by 141. 100 times, what do we have as VS? So 1000 divided by 141. How much is that? That's it.
I was just doing it wrong, I guess.
Were you on question 8? Yeah, that's probably the two. It's quiz 7. No, I know this was 7. This week was 7. Just send me an email right now, and then I'll